Okay, hello Nidir. I just thought I'll make a short video on the alternating current chapter as well. It is really simple and it extends on the ideas that we've already talked about. So the first key idea that you understand is alternating current means um, it alternates between plus and minus, right? So one common form is it takes the sinusoid current. So what that means is the current goes up, the current goes down like a sinusoid, right? So this is your current. It takes this form I equal to I naught sine omega t. Here let's understand all the terms that are involved. So I naught is the height. So I naught is what we call the peak current, right? And omega is the representation of omega is 2 pi f. So if you calculate say omega by 2 pi, then that gives you the frequency of the wave, right? And like if you want to find the time period from here to here, right? So that time period will be 1 by f, right? So this in a way is called angular frequency, and this is just called frequency, right? So these things we already know. So the idea is that in alternating current, the current fluctuates between plus and minus, and a general form for this can be written in terms of I and I naught and omega, right? And t is your free time variable here. That's varying, right? So that's your t. So it looks like a sine theta in a way, where theta is omega t. Okay. So that's one of the key first things that you understand here in alternating current. Then what we also saw is in a generator. So like recall that a generator is set up such that there is constant field, V field, and the coil inside this is attached to something that rotates, right? So what we noticed was uh, the when it is completely flat right now flux is zero, right? So but d phi by dt is maximum here. So at this point maximum amount of EMF is being generated because it's starting to turn, and then it starts to drop and it comes down to zero when it becomes completely like 90-degree parallel, and then comes back down to the other side. And so this is the induced EMF, right? So that is what we saw from the last chapter, right? Induced EMF V, which is was equal to minus d phi by dt, right? From the previous chapter, and this is also changing with time. So what we can see is you also have an alternating voltage, not just alternating current, right? So V can also be written as V naught sine omega t. So this is V naught, and that's varying at sine omega t, right? So that's the key idea. So in a generator like setup, we notice that in an alternating, we also observe alternating voltage, right? So both current and this thing can oscillate. Uh, so that's another idea. Okay, so one just small thing here, like if you get this CRO sort of questions, we saw this last year as well. If you get these CRO sort of questions, and if you're represented, if you're given gain or sensitivity in these questions, like CRO questions, so you will be given as Y gain or an X gain. What that means is that there will be some calibration factor, so that will look like 2 volts per centimeter. And say if your height here you can see is, so if this one box is 1, so this is height is 2, right? So height is 2 centimeters, that's equal to, by this conversion factor which is called gain or sensitivity, so you can say that that's equal to, of course that's equal to 4 volts, right? So this is 2 centimeter, which is actually equal to 4 volts, right? So this conversion factor is used to convert these graphs that you get on instruments, or the CRO is one of those instruments that tries to measure the current, the voltage, but it gives you in terms of centimeters, and you'll have to use some conversions. That conversion is called gain and sensitivity. Okay. Again, just refer to your book for more details. I'm just pushing through here a little bit. Okay, then the only key main idea here is to have something we call the RMS current or RMS voltage, right? So what we say is, because in your in every house right now you have alternating current, right? So it oscillates between plus and minus, but as a result like the bulb is still lighting up, so it is consuming some power, right? So we ask what is an equivalent DC voltage. So this is in the AC scenario. In the DC scenario, if this is the zero line, we would just give one constant voltage, right, throughout. So we ask for the power of AC to be equal to power of DC scenario, right? So we are not changing current. What is the, if this is V naught, then what is this VDC level that we should have so that the powers are the same, like the bulb glow equally brightly. What is the DC power I should give for a specific V naught power, right? So the question is what is VDC level which gives the same power? For the same power, what is this VDC level, right? If my this peak, this thing is V naught, VAC ka peak, what you noticed, right? So the answer to this is VDC is V naught by square root 2 actually. So like it is roughly zero point 0.7 times V naught. So if you, so this is an average of 0.7 times V naught. That is equal to your VDC level. So if you supply that much, uh, then it is the bulb will glow same, which is DC and equivalent. The reason why we draw these equivalent scenarios is because we already have formulas for power in DC, right? Like V square by R, V into I, or I square R. So if we know this equivalent power to convert from AC to DC now, before using these formulas which are for the DC regime, right, we can just simply convert our AC power first. So if say our peak to peak, right, is 2 V naught for AC, then peak to 0, right, so peak to peak is double the amplitude, right? So peak to 0 is only this much, so that's V naught for AC. So that can be now by converting can be written as V naught by square root 2, which is 7.7 V naught for DC. So now that we know this, so the power that was consumed, so that will be V naught by 2 whole square when by R. Say it was fed into some resistor, right? By square root 2, sorry. So it becomes V naught square by 2 times R. So this is the key idea. Like this is how you can convert AC power into DC power, into say equivalent. Like you can use these formulas to convert it into. So remember that you don't just put the value of V naught here. You convert it by root 2 because you make it 70% and then you take. Okay, and similarly we have the same concept as, so these are called the RMS current. So what you notice is the RMS voltage is V peak to peak, V peak voltage, whatever is the peak, or V naught, that was the case, by root 2. Similarly this is I peak voltage by root 2. Alright, so in case you want to use current, that is the case. So let's just see where this thing is coming from very quickly. Like, so if your current is oscillating like this, right, above 0, it goes plus and it goes negative. So plus IP and minus IP, right? For power we need that power is proportional to I square R, right? So if we square both of these, then that baseline still remains there. This 0 point stays at 0, but this IP point becomes IP square, right? So this again point becomes 0. This is 0. So the way it works is it goes up, right? Then it comes down, then it goes up, then it comes down, because it needs to peak at, so the square of the minus side and the plus side is the same, right? So this IP square and this IP square is the same. Both of them go to the same point, come down. So it looks like it forms a sine wave, but it is always above 0. This is this, I'm plotting I square here instead of I that I was plotting with time here. I'm plotting I square because you need I square R here, right? R is just a constant, so I'm not multiplying it. So I square graph you will see is centered at around IP square by 2, right? If the peak is IP square, so it's a square graph. So the middle point is IP square by 2. So the average power is kind of IP square by 2 times R. This is your average power. So that tells you that IP must be IP by square root 2R. So like in a way you can see that if I take I as IP by 2, IP by square root 2, then it just becomes the similar formation. Like this whole thing I'm trying to tell you is how we arrive at this RMS current, but derivation is not really that important. All you need to remember is you need to convert from AC, whatever that height of AC is, by square root 2 before you use any of these formulas. Okay, if you understand that, that's good. Uh, okay, so the last concept is called rectification. So rectification is about converting AC into DC. So AC goes like this, and ideally we want to get just a single. If this is V naught, we want to get V naught by root 2 out. Right. So the question is how do we do that? So the step one to do that looks something like this. So what we do is we attached. So this is where our AC signal is coming in. Right here we have a diode and we have a resistor here. So the main component here is a diode. So remember what a diode does. Diode only lets you one side of current to pass through. So if you have say an AC signal like this, then all the negative signal, right, so tries to make the current flow opposite to the diode. So this lower portion diode cuts that region off. So the graph looks like something like this. So this is what I'm plotting here is V out, which is the voltage drop across this guy, across the resistor with time, right? Or it should have copied the signal fully, but it only does what we call half rectification. Like in the sense, at least current is not going the other way, but the problem is it's not also giving us anything, right? So let's do another improvement on top of this, right? So a secondary improvement on this looks something like what we call a bridge rectifier, right? So in bridge rectifier, instead of one diode in a simplistic formation, we have four diodes. I'll be done in 5 minutes. Yeah. So we place four diodes in this formation, that 1 and 4 are in the same direction, and the other two diodes, uh, 2 and 3, are in the other direction, right? And whatever you get out of it, like these middle points are attached to a resistor, right? So let's see, your AC signal is your sinusoidal signal, right? So when the current is say trying to flow like this, trying to come out like this, then it has a path where it won't try to go towards this because this is opposite to the flow, so it goes towards 2, right? Then can't go towards 4 because that's blocked, so it goes through the resistor, goes here, it goes towards this 3 terminal, it comes here. Now it can't. hmm, Now it just goes towards 3 and then back out, right? So in this path, when it's trying to flow towards this, it flows through 2 and then 3 out, right? 2 resistor, 3 and then back home. In the other scenario, it goes so instead of coming from the 1, it comes up from the 3 side, then it goes to 4, then the resistor, then it comes to this point, then 1 and then home. So there are two paths through which, but notice that current always flows down from the resistor, right? Current never switches direction from the resistor itself. So what happens is in this first region, second region, then again first region and second region. In the first region, you have 2 resistor 3 and then back out. In the second part it flows through, it enters from the bottom which is 4, then resistor, then 1 and then back out, right? So that's the key idea. So two different mechanisms are play, but I direction to R is always the same. So what that means is, for an input wave that comes like this, which oscillates between plus and minus, what you get out at the end is a wave that kind of just bounces because of this what we call the 4-bridge rectifier or the 4-diode rectifier. Not a 4-bridge, just a bridge rectifier or a 4-diode rectifier. If you add just one diode, it just cuts this middle portion off. But here in this case, we get the signal which bounces only on one side. So that we are getting somewhere. Okay, another advanced idea in this area, we don't want this much bouncing also to happen. So what we do is something uh, like this, where we bring back the first setup where we had a diode and a resistor, right? This resistor, but instead of this, we also add a capacitor, right? So what that does again, so when the positive half of the cycle is going on, the diode is basically like allows current to pass through, right? On the back side, what we noticed was it wasn't allowing to pass through, right? So let's see how that helps. uh, Now adding this capacitor, how does that help? So in the positive half of the cycle, the current will try to flow in and it will try to charge this capacitor up, right? So originally it charges the capacitor up to the peak voltage, whatever that is. So what if this is V0, it charges the capacitor to V0. After that, when the voltage tries to decrease, the capacitor also has to try to discharge. So it tries to discharge itself through the resistor path, right? Like it tries to shorten itself. But what happens is it's not able to discharge very quickly. The signal changes down, right? Signal is reducing to zero, right? But what happens to the capacitor? It can't reduce so fast, so it tries to discharge slowly. But and it discharges till this whole negative cycle is passed when the diode is cut off, and at that point it charges up again, right? And at this point when it is trying to discharge again, it discharges slowly, and then it charges up again, and then discharges slowly, charges up again, discharges slowly, right? So there are two mechanisms at work. One is the discharge mechanism, and one is the charging up mechanism. This is right. So when charging is happening, so this happens first, right? This second phenomena happens first, and then the first thing happens, then the second thing, then the first thing. So in the first thing, diode is allowing current to pass through, and this means that capacitor is storing charge. Is storing charge, right? So when it is storing charge, it is gaining some voltage, so which is why this area is there, right? All of these areas where it is climbing voltage. But then when it tries to discharge, right, in that case, the diode is disconnected, is open, because the current is trying to flow opposite way, so it kind of like breaks the circuit here. So none of the left side is important. So uh, it just becomes a capacitor and a resistor essentially, right? So the diode is open, right? So capacitor discharges through the resistor, right? But this discharge is very slow, right? So because it is slow, it is slowly only reducing, right? But because of this, it comes back alive after some time. So ultimately, what you get as your input waveform is a AC signal, but the output waveform is what we call like partially rectified segment, right? It climbs up, then comes down, climbs up, comes down, climbs up, comes down, climbs up. So this, in a way, is what we are looking for also, right? Like we are looking for ideally a constant voltage at around 0.7 V naught, but what we get is this slope lines out, right? Which is kind of like close enough to what we get. There are more advanced techniques even to smoothen this out. So this is called smoothing, right? So this is the key idea here. So there are more advanced techniques here, but we will not go into that right now. I think this is the last thing that your chapter talks about. Make sure you again do the questions there. I am going through things a little bit fast for the sake of time. Make sure you understand then what is happening there, and we can always discuss your questions. So yeah, do all the work questions and internal questions there. Okay, see you.